So third problem in Hartnell governor. So please read the question very carefully. A spring-loaded governor of Hartnell type has arms of equal length. So what does this tell you? Arms of equal length, x is equal to y. First, from the first line, you can take x is equal to y. Okay. The masses rotate in a circle of 130 mm diameter when the sleeve is in the mid position. Okay. So therefore, mid position means your arm is vertical. So that represents r. R is equal to d by 2. Diameter of that circle is given, circle of rotation. So 130 by 2 will give you the radius. Okay. R. Pivot point radius. And the ball arms are vertical at this mid position. Okay. The equilibrium speed for this position is 450 rpm for this position. Clear? Mid position, average speed position, 450 rpm. Neglecting friction. The maximum sleeve movement is to be 25 millimeter. This is h. And the maximum variation of speed taking into account the friction is to be 5% of the mid position speed. So plus or minus 5% can vary due to friction at the same sleeve position. Okay. So the mass of the sleeve is 4 kg. The capital M is given in this problem. Okay. Sleeve mass is 4 kg. And the friction may be considered to be equivalent to 30 Newton. Friction is also given. The power of the governor must be sufficient to overcome the friction by 1% change of speed either way at mid position. Okay. Determine neglecting obliquity effects of the arm. So don't worry about this sentence. Next problem you will see what is obliquity. Okay. Value of each rotating mass. Small m is not given in the question. What is the value of small m? First question. Okay. Spring stiffness in Newton per millimeter. Small s. Initial compression of the spring. Capital S1 by small s. All these things we are going to find out. So list down the given data. So x is equal to y. In the first line itself it is given equal arms. Okay. So diameter of rotation 130. Therefore radius of rotation for the this position, mid position. So low speed position is this, high speed position is this. Because your ball is here, for lower speed the centrifugal force will be very less. So it will be inside. For a higher speed the centrifugal force will be large, therefore it will go outside. Because this is a single piece of steel, therefore when this arm swings, this L also will become perpendicular to that position. So 90 degree, when it goes out also 90 degree. Okay. 65 rpm is 450, convert that into omega 47.23, h is 25 millimeter, m is 4 kg, I mean the sleeve mass, capital M is 4 kg, friction force is 30 Newton, small m you are going to find out, it is not there in the question. Okay, right, let's move on. So value of each rotating, small m I am going to find out. First question, let small m equal to value of each rotating mass, capital small s, so this is not capital, this is small s. Okay, so if you want you can write like this, small s is equal to spring constant. Okay, spring force on the sleeve at the mid position. Okay, this is not small s, this is capital S only. Okay, S1, S2, that is at the mid position, this is capital S. At the lowest speed it is S1, highest speed it is S2, that is I am writing. Okay, since the change of speed at the mid position to overcome friction is 1% on either side, so minimum speed at the mid, see, please understand this very carefully. The friction 30 Newton is such that let us say I am going around at 450 rpm. So at 450 rpm, for plus or minus 1% change in speed, the governor is unable to move the sleeve because of friction. That is the meaning of this. So 450 rpm, what is 1% of 450? 4.5. So 450 minus 4.5 plus 4.5, the sleeve will not move, it will be in the same position because of friction. If there is no friction, for each change in rpm, the sleeve will move accordingly. But because of friction, at the equilibrium speed, plus or minus 1%, the sleeve is not moving. Okay, that is the condition given. So minimum speed at, so that plus or minus 1%, so minus 1% is the minimum speed at the equilibrium position, plus 1% is the maximum speed at the equilibrium position. Beyond that, if you go, the sleeve will move up or down. Okay, so that two extreme speeds for the given sleeve position I am finding out. So omega minus 1% of omega, so 0.99 omega, so that is 46.6 radians per second. It will remain vertical. The x arm, the vertical ball arm will remain vertical for 46, from 46.66 radians to maximum. So maximum what? So omega plus 1% of omega. So that is 1.01 into 47. So from 46.66 radians to 47.6 radians, the arm will remain vertical. It will not go left or right because of the friction at the sleeve spindle interface. Okay. So each speed it should vary normally, but friction is stopping from this to this. The X arm is remaining vertical. It is not swinging left or right. Okay. Centrifugal force at this minimum speed. So these two, please remember, these two have same radius of rotation, 130 by 2, because there is no change in the spindle position. So therefore this remains same, 130 by 2, 65 millimeters. Same radius for both the speeds. So use the same 65 mm radius and find the centrifugal force. Only the speed will be different. M omega square r, M omega square r. R will be different. Omega will be different. R will be same. Okay. So FC1 is a minimum speed case, 46.6 radians case. M is unknown. Keep it M itself. Omega 1 is 46.6. R is 65 millimeter. Okay. So M 46.6, 65 millimeter, 141.5 M Newton. This M is also there. This is unknown quantity. Okay. Keep it as it is. Similarly for higher speed, 47.6. So here what is the important thing you have to note down is both the FC1 and FC2 will have the same radius of rotation. Because of friction, it is remaining in the same position. Similarly for the higher speed case, so FC2, as I told earlier, M is unknown, keep it as M itself. So this is 47.6, this is 65 millimeter. So this thing, if we cross multiply, we get 147.3 M Newton. Okay. So we know that for minimum speed at the mid position, so this formula, so S plus mg. So I have told that load on the spring is, I have declared as S, not S1 or S2. At the mid position it is S. S into mg minus F. So minimum speed, minimum position means minus, maximum position means plus. Okay. So minimum position S plus mg minus F equal to 2fc1 into xy. Do you understand why minus plus? Friction at the lower speed it will be minus, higher speed it will be plus. So M is sleeve mass is 4 kg, friction is 30 Newton, FC1 is just now we have found out 141.5 M Newton. Okay. So X is equal to Y, no problem. X and Y will get vanished. Therefore, I can write like this. So S plus 4 into 9.81 minus 30 equal to. So with this I can form an equation. S plus 9.24 equal to 283 M. Clear? Similarly, for the second case, I am forming another equation. For maximum speed case, S plus mg plus F equal to 2fc2 xy. So put all the numbers into this. 4 kg, 30 Newton. So only difference between these two formula, this minus is plus here. No other difference. FC1 is FC2 here. That's all. All other things are same. Okay. So 4 kg sleeve mass, capital M is 4 kg. This is 30 Newton. This is 147.3 M. Just here, it's here only you have calculated that. Okay, 147.3 M. M is there. Don't forget this M. This is Newton unit. Okay. So put all the numbers into that. X is equal to Y. Therefore, the fraction will become 1. So put all the numbers. Capital M is 4 kg. So this is 9.81. This is 30 Newton. 2 it FC2 is 147.3 M. So this fraction will become 1. So simplify this, you will get another equation. So S is equal to S plus 69.24 equal to 294.6 M. So using this I am going to solve for M. I will eliminate S using algebraic elimination method. Use the two equations and solve for M using algebraic elimination method. I get M is equal to 5.2 kg. So that is our first question is answered. Ball mass is 5.2 kg. Okay. Second question. Spring stiffness in Newton per millimeter. Let S is equal to spring stiffness in Newton per millimeter. Since maximum variation of speed considering friction, this is the second case. Okay. Here, one important thing I want to tell you now. So there are two conditions given in question. Okay. For equilibrium position, okay, for equilibrium position, vertical position, plus or minus 1% speed of that equilibrium speed, 450 rpm, the sleeve is not moving. So now that entire thing is over. Now you should not consider 450 rpm or 1% or anything related to that. Now this is totally different second part of the problem. Forget everything you have done up to this. Now second part of the problem, because when you are doing centrifugal force, you will think that you have already calculated centrifugal force. Let's go back there. No. Now the radius is changing, RPM is changing, everything is changing. Therefore, second portion, this 5% portion, 1% portion is over. There is no change in speed there. No change in radius. From 46 point something to 47 point something, no change in sleeve position. Here the sleeve position is changing. Second case. Okay. So totally forget the first portion of the problem. Second portion of the problem. Because when I was doing this PPT, I thought I already calculated centrifugal force. Why should I again calculate centrifugal force here in this second portion of the problem? Here radius is different. The angular position of the XY arm is different. Everything is different. Therefore, FC again you have to calculate. Okay. So since the maximum variation of speed considering friction is plus or minus 5% of the mid position speed, therefore, like from this you can easily find out 450 rpm or 46 point something is the mid position. Therefore, minimum speed is 95% of that. I'm going to call that minimum speed as omega 1 dash. Okay. So that is 95% of omega minus 0.05. Okay, 95% of omega. So 95.95 into 47.13, it is 44.8 radians per second is the minimum speed case. Okay, maximum speed 1.05, 105%. So that is 49.5 radians per second. Now for these two omega, I am going to find out the centrifugal force again. Okay, so whatever centrifugal force you have already calculated is different. That is for same radius of rotation. Here the radius of rotation is different. Minimum radius of rotation considering friction R1 equal to R minus H1 into X by Y. So R is 65 millimeter for the vertical case. Okay, H1 is 20, H is 25 millimeter. It is given in the given data. Okay, 25 millimeter sleeve lift. Now I am going to take half of that as, this is general assumption. Okay, half of that as H1. H2 is another half. Okay, why I take half? See here, this is equilibrium position. For a low speed position, it will be like this. Okay, I will overlap this only, then you will understand. So initially, minimum speed, the ball will be inside. Okay, equilibrium speed, the arm will be like this, 450 rpm. For a high speed, it will be like this. Same L arm is in 3 positions. Now this entire thing is 15 millimeter sleeve lift, 15 millimeter. So what I am going to do, half on the upside, half on the downside I am taking. Clear? So this is my H1, this is my H2. For low speed case, your arm will come below like this. This is H1. For high speed case, so this is the low speed case. High speed case, it will be like this. So this is H2. So total H is 15. Out of that I am taking 25. Out of that I am taking half as the H1 and half as the H2. Okay. So X is equal to Y. So find out R. 65 millimeter minus 25 by 2. Okay. So minus is repeated here. There is only one minus. Let's make this single line. So 25 millimeter by 2. So that comes around 0.0525 millimeter. Okay. Meter. 52.5 millimeter. Okay. Maximum. So R minus H2 into X by Y. R2 equal to R minus H2 into X by Y. That is also going to come around the. So I am going to add that to the radius of rotation. Why you are adding and subtracting? So please look here. So axis, governor axis. So this is R. Okay. So when the ball comes inside, your radius becomes smaller. When the ball goes outside, your radius becomes larger. Okay. So from R, I am finding this value and subtracting. That is this one. So from R, I am finding this value and adding. So that is, this should be plus. So that is this one. Okay. So it is greater than the mid position, radius of rotation outside. So 0.0775. Any doubts in this? Why we are doing this? So this is the equilibrium position. So minimum speed position from the governor axis. So this is smaller than this. So therefore, find out this value and subtract it from radius of rotation. You will get the small low speed radius. Similarly, for high speed radius, find out this value and add it to this radius. you will get the R2. So that's what I am doing here. Clear? So R1, R2 we have found out. So centrifugal force Fc1 dash m omega 1 dash square R1 5.2 kg ball mass omega 1 dash you have found out in the previous slide 5% minus, okay, 44.8 radians. So R1 just now you have found out as 52.5 millimeter. Find out the centrifugal force. It comes around 548 Newton. So any confusions here? Why we are doing this again? Y plus y minus. Okay, this should be plus. Here. Similarly, Fc1 dash is 548 Newton. Second case, centrifugal force at the maximum speed. The Fc2 dash, so mass is 5.2 kg, same for everything. 49.5 plus 5% speed of the equilibrium speed. 49.5 radians. So second radius is 0.0775 meter. Okay. So put all the numbers, we will get 987 Newton. So Fc2 dash is 987. So let S1, S2 I am going to find out, then only I can find out the spring stiffness, S1 minus S2 by H. Okay, so S1, so general formula, S1 plus mg minus F for the minimum speed case. So S1 plus mg minus F equal to 2 Fc1 dash into x by y. So all the values, sleeve mass is 4 kg, friction is 30 Newton, Fc1 dash is 548, just now you have found out in the previous slide. So x is equal to y, substitute all the numbers, you can find out the value of S1. So S1 equal to 1086.76 Newton. Please look at this calculation step by step. Right, I don't have time, so I am going very fast. So please look at it carefully. 4 kg, G is 9.81. So friction is 30 Newton. For the low speed case, I am putting minus here and Fc1 here, S1 here. Okay. So x by y become 1. This fraction becomes 1. 2 into Fc1 1 dash is 548. So it's all I'm simplifying. I am getting S1 equal to 1086.76. Similarly, for second case, high speed case, S2, this friction will become plus, this Fc2. That's all. All the other values will remain same. Substitute the values. So S2 plus mg plus friction equal to 2 Fc2 into x by y. So why I am putting plus and minus for friction? This I already told you in the beginning itself. When your sleeve is moving down because of low speed, your friction will move up, which is opposite to the sleeve mass direction. Therefore, for low speed case, we are putting minus for friction because weight direction, friction direction. For a high speed case, your sleeve will move upwards. Therefore, your friction with the spindle will move downwards. It is in the same direction with the weight direction of the sleeve. Therefore, you are going to put plus here. Clear? That fundamental is going to remain same everywhere throughout the governors. So high speed case S2 mg plus friction. This m is capital M, sleeve mass equal to 2 Fc2. Higher speed centrifugal force in x by y. Okay, so 4 kg 30 Newton Fc2 dash. So x is equal to y. All those values you substitute into this equation. So therefore sleeve mass is 4 kg, gravity 9.81, friction 30 Newton with a plus sign in the middle. Fc2 dash is 987, x by y fraction because x is equal to y it becomes 1. So solve this for, this is S2. Okay. So S2 is equal to 1904.76. So we know that stiffness of the spring is S2 minus S1 by H, S2, S1, H. So therefore substitute in millimeters itself, you will get the stiffness value 32.72 Newton per millimeter. So stiffness of the spring is 32.72 Newton per millimeter. Okay. So initial compression of the spring S1 by S. So S1 is 1086.76. Stiffness just now you have found out 32.72. Initial compression of the spring is 33.2 millimeter. Clear? So that completes the problem. Let us summarize the results. Value of each rotating mass is 5.2 kg. Stiffness of the spring is 32.72 Newton per mm. Initial compression of spring is 33.2 millimeter. This is taken from your Kurmi textbook 18.15 problem. Okay.